chances do she need to win these 3 prizes? Okay. Well, she gotta have at least 3 chances, right? Because like, okay, I don't know, maybe you don't know this. Let me explain. So like, she has to guess the price of this prize. She has to write it there, and if it's right, it'll say until it's right. Then she gets to go to the next one. But if she's wrong, this will shift over, and then she use chance number 2 to try to win that prize. You see what I'm saying? So she has to guess the correct price for those prizes. She has 10 chances to try to win as many prizes as possible. Okay. All right. So the question is, if your random variable is how many chances you need to win these prizes, what's the best case scenario? She needs what? 3 chances. That's the minimum. You can't win all 3 prizes in one chance. You can win, use this chance to win that, use this to win that, use this chance to win that. So you gotta use at least 3. Is everybody with me so far? The worst case is she needs all 10. Is everybody with me? So, I need to erase her head. Okay. So this random variable, would look like this. So X represents how many chances you need. How many chances? Number of chances. And then the probability of X, you would put here, we'll see this in a moment, but you will put here the probability of needing that many chances. Is everybody with me so far? So the best case scenario is you need 3 chances. But she could either need 3, 4, 5, 6, 7, 8, 9, or 10 chances to win. Is everybody with me? Because this is a finite list, the list started, the list ended, this would be a discrete random variable. Is everybody with me? So the answer is yes, this is a discrete random variable. Is everybody with me? Now, how would we get these probabilities? Well, remember we talked about you can get these probabilities by looking at past data, retrospective study, look at what happened in the past to predict what will happen in the future, right? So we could collect the data of contestants that played this game in the past, calculate their relative frequencies, get the counts, convert the counts to relative frequencies, and those relative frequencies could be the probabilities of, you see what I'm saying, of using 3, 4, 5, 6, 7, 8, 9, or 10 chances. Okay? All right. What about this one? Time is money. Like if we were looking at if X was the random variable that says how much money you won, would that be more discrete or continuous? More continuous, right? And I don't know if y'all remember when I said this. When we were talking about quantitative versus qualitative, and then I said with the quantitative there was either what? Discrete or continuous, right? Remember I told you if there's more than 10 possible values, you can push it to the continuous realm. Same thing. So because there's so many possible values of winnings, the worst case is 0, but you can win $1, $2, $3, $4, all the way up to what? $20,000, right? So there's 20,001 possible values. You can treat that as a continuous variable because there's just so many possible values, right? Yes, I could. Now, legally, that is a discrete random variable, okay? But because the list is just enormous, you can, make it continuous, okay? So in this case, no. Okay, this is more continuous than discrete. So when you have, less than 10 possible values, discrete. Once you go past 10, you can take it into the continuous world, okay? Now, if the question was, now for those of you that are Price is Right enthusiasts, if the question was, with all contestants, how many products did they put in order here in the correct section? Now that will be discrete, because the worst, and how many products are worth 5? I think there were 5, right? And time is money, I think it's 5. She's very happy. Okay, I think there's 5. It's either 5 or 6. 5, let's say it's 5. So the worst case scenario is, here. So if X was the random variable representing, no, I see you, I'm gonna get to you. So if X is your random variable representing how many products were sectioned correctly, now the worst case scenario is none of those products were put on the correct pedestal. But she could have gotten 1 right, 2 right, 3 right, 4 right, or she get all 5 right. You understand? So because there's only 6 possible values, this is more of a discrete random variable. Does that make sense? And then of course, P of X is say, well, what is the probability that you get 2 of them correct, or 3 of them correct, or 4 of them correct, or all 5 correct? Now, so yeah, go ahead.
Is there, besides the numbers being more than 10 values, is there another like indicating factor that it is?
Yes. If you have possible values that are also going into decimal places, that's also, you want to treat that more continuous than discrete. Yeah. Good point. Very good point. You think you slick?
Me?
Yes.
What did I do?
In a good way. In a good way. Did you have statistics?
I took
AP?
No, I took a class called Function Statistics and Trigonometry.
And you covered a little statistics.
Mm-hmm.
Yeah. I could tell from different questions that some of you asked, I'm like, you had statistics. You hustling. In a good way. I mean it. Yeah. No, good point. Thank you for bringing up that point. Very good. All right, what about this one? The difference in the contestant's total and the actual total on checkout. Some of y'all just, let's have a little fun. So this contestant has, oh, she has to. Okay, so she has to guess the price of these products, and then they're added up to make a total. Her guess for total price. And then they show the actual price, and then that's the true total. And if her total is within what, $2 of the true total, then she wins the game. Is everybody with me? So she's happy because she was within 35 cents of the that was the grand total, and she was only off by 35 cents, right? So would that be more discrete or would that be more continuous? Well, it's a little bit more continuous because the different actually for this one, think about it. Yes, she wins if she's within $2. That's the object of the game. But a contestant could be off by $5.32, $2.14, $20.80. You see what I'm saying? So because there are like more than 10 possibilities, you see what I'm saying? The best case scenario is she's on the nose, so 0. But she could be off a penny, 2 cents, 3 cents, blah, 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 $1, $1, $2, $3, blah, 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 $10, $10.01. You see what I'm saying? There's so many possible values. So this is more continuous. Okay, so how will we, so going back to the definition of continuous, it said a variable is continuous when there's just so many possible values where the only way to list them all is to use interval notation. For this case, if X represented the difference between the contestant's total and the true total, the difference, then the only way to list them all is I would have to say, let X be the continuous random variable where X is greater than or equal to what? 0. Because you can't be negative. You see what I'm saying? It's the absolute difference between the contestant's total and the real total. So the only way to list all the possible values that X can take on, I have to use interval notation. And that would be the best way to do it, is to say X is greater than or equal to 0. Okay? Now, of course, y'all know you can rewrite that as 0 to infinity. Okay? But this is fine. This is good enough. Okay? So that would be more continuous random variable. Okay? All right. And then the previous one that we said was no also. The only way I can write that is to use interval notation. I would say that X can take on values between what? 0 and $20,000. You see what I'm saying? So let X be the continuous random variable that takes on values between 0 and 20,000. Okay. All right. Okay. Did I have another one? Oh, here's another one. Okay. This ain't checkout. This is 3 strikes. Oh, crap. Oh, but still, I like this. I like this one. What did I say? Oh, what I meant to have here, I'll correct it. Let's correct it right now. Oh, man, I got a typo. Copy and paste got me. Okay? Here. The number of strikes pulled before winning the pricing game checkout. Oh, no, not checkout. What is this? 3 strikes. 3 strikes. Sorry about that, y'all. Make that correction. Yeah, I copied and pasted and forgot to make correction. Now I can't remember what I put behind that sign. Let's use that one. Let's use that. The number of strikes pulled before winning the pricing game is 3 strikes. I hope that's correct, what I put up on. But if I remember, I think that's what I use as my. So this is my random variable. Let random variable X represent the number of strikes pulled before you end up winning. So what's the best case scenario? 0, right. She pulled out, got something I don't know. So there's this big baseball, and inside are the digits to the price of the card, and there are 3 strikes. Her job is to pull out the numbers in the price of the card and say where they go, and you got to fill these in before you get 3 strikes. You pull the 3 strikes out of there, you're out, you lose the game. Is everybody with me? So you're right. The best case scenario is no strikes. She don't pull out any strikes, and she fills in the price of the card. Is everybody with me? So X, the lowest value that X can be is what? 0. What's the worst case scenario? 3, right. But she could have won the car. She could have won the car. She got 1 strike or 2 strikes. So X can take on the values of what? 0, 1, 2, or 3. Is everybody with me? So with that would be more discrete, wouldn't it? Right. Now I just pray that says yes. Yes, thank you. Okay. Because I was trying to remember if I remember this was the question I forgot. Let's change it. So that'll be more discrete. Okay. Does everybody understand so far? All right. Did I have another one, or that was it?
That's it.
That was it? Okay. All right. So do y'all understand the difference between discrete and continuous? Okay. Let's move on. All right. So when you create a relative frequency table, notice when I say relative frequency table, I'm actually saying when you make a probability distribution, because now we're in the futuristic term, probability distribution, okay? So even though the data that's here is based on retrospective study, we're saying that these results are predictions of what we believe will happen in the future when we conduct the experiment. You understand? So we're using past data to say what we believe will happen in the future. Okay, so that's the reason why I say with the random variable, and this is the difference between that separates a relative frequency table versus a probability distribution table. Is everybody with me? Is this concept. Okay, so when we talk about probability distribution, we're saying what is the likelihood of like this outcome happening in the future if we do the experiment. Is everybody with me so far? So the procedure was not performed yet. You listed all the possible outcomes, and you're creating either a t-table, or I have to give you if I don't use past data, I have to give you a formula that will help you calculate those probabilities. So in this PowerPoint, we're going to look at, well, what if we looked at past data, right? But then, as we transition to part 5.2, we're going to say, no, what if we have a formula that can model the behavior of this experiment? Okay, and we're going to see that case later. Okay, let's look at our first example. In the pricing game Bonkers, the contestant must determine whether each digit in the incorrect price is higher or lower in a certain amount of time. So this contestant, sucks. Yeah, she got that wrong. Okay, so in this game, she has to race over here and then put these on like either above or below the number based on if she believes that that digit is higher or lower. She has 30 seconds to do it. So she has to race over here, put it in order, come back, press this button. If it says then that means she knows at least one of those is wrong. She has to go back, make changes, and she has to keep doing that, racing like that, until she gets it correct, okay? Or the 30 seconds expires. Okay, assuming random guessing of the digits, how could a discrete random variable be used that represents the number of correct digits? So if I were to make a discrete random variable, I would say let x be, it says let x be the random variable that represents the number of correct digits. Number of correct digits. What's the worst case scenario? What's the worst case scenario? What's the lowest value that x could be? 0, right. You don't get any of them right. 0, right. What's the best case scenario? 4, right. She gets all 4 right. So of course, she could also get what? 1 right, 2 right, or what? 3 right. So if we were to make the t-table, this is what we will start with. 0, 1, 2, 3, and 4. All right? Now, again, how do we determine the probabilities? Okay? How will we determine like the probabilities? I'm glad you asked. We're actually I think we're gonna use this in this section and the next section. Now, I said, let's assume that she just randomly guessed. First try, she just randomly guessed. So here's what I want you to do. I know we're coming closer to the end. I'm gonna demonstrate something to you. I'm gonna demonstrate how we could theoretically create that probability distribution. So I told you that we could look at past data and look at the proportion of times that they got none right, 1, 2, 3, or 4 right, and to determine these probabilities. But what if we took the theoretical case? We looked at the theoretical case of getting of this scenario. So take a look at this sample space. So H, let's say H represent higher, which means you put it above, and then L means lower. Is everybody with me so far? All right. What was the answer to that, by the way? What was the answer to that? It was high, low, high, high. Okay. All right. So we already said we know X is taking on value between 0 and 4. Now, what we could do is just map. You see what I'm saying? Like here. So these are all the possibilities of putting those little discs in those spaces. Okay? So this outcome here, if she would have did low, high, low, low, she wouldn't have gotten any of them right. You understand? So I'm going to map this to the value 0. Now, do y'all see that there's 16 possibilities, right? There's 16 possibilities. Because think about it. The first digit, you either choose higher or lower. So there are 2 possibilities. The second digit, 2 possibilities, higher or lower. Third digit, higher or lower. Fourth digit, higher or lower. So 2 times 2 times 2 times 2. So there's 16 possibilities. Is everybody with me? Now, if this outcome, if she would have put those discs in this order, she would have gotten none of them right. So, and that's the only case where you get none of them right. So I'm going to map this to a 0. Is everybody with me? I'm going to map those to a 1. Because if she would have done any of these, she would have only gotten 1 right. Is everybody with me so far? Like here, low, high, low, high. Low, high, low, high. She would have gotten the last digit right. Is everybody with me so far? And like this one, high, high, low, low, she would have gotten high. She would have gotten the first one right. This one would have been right. But nonetheless, these get mapped to 1. Those get mapped to 2. Because if she would have chose any of these combinations, you would get 2 right. Like for example, low, high, high, high. Let's see, that would be wrong, that would be wrong, and these would be right. Because the solution is high, low, high, high. So she would have gotten these 2 right and these 2 wrong. So that got mapped to a 2. These others are mapped to a 2. You see what I'm saying? Because you would have had 2 right. These would have been mapped to a 3. right? Because look, this one, you would have gotten the second digit wrong. This one, high, low. This would have been wrong. You see what I'm saying? So these, if she would have chose those, they would have been mapped to a 3. And then finally, this one is the correct answer. High, low, high, high. So that would have been mapped to a 4. Is everybody with me? So I'm showing you I'm showing you the theoretical approach of how to create a probability distribution.